Welcome to Section 1, Lesson 8. Today is the marathon, where we put every Section 1 skill to work in a single sitting. We will solve mixed expressions that combine the number line, order of operations, absolute value, both sets of exponent rules, scientific notation, and estimation. Each problem will require you to recognize what kind of expression you are looking at and reach for the right rule on the spot, the way a seasoned algebra student does without hesitation. Marathon style practice is essential because real-world problems almost never come labeled with which lesson taught the relevant skill. A mixed expression in chemistry, a compound interest formula in finance, or an engineering tolerance check all combine several skills at once, and the only way to handle them fluently is to have practiced the combination in a setting where the labels are not given to you. That is what this lesson does. Every problem in the marathon is deliberately constructed to require at least 3 distinct skills from the prior 7 lessons, and the worked examples will demonstrate the strategy of recognizing structure first and applying rules second. First idea on the board. By the end of this lesson, you will have practiced all 7 Section 1 skills together in one continuous workflow. Until now, each lesson has presented one skill in isolation. The marathon shows that real expressions almost always require 2 or 3 skills working together, and the trick is to apply them in the right order. The order is not arbitrary. PIMDS dictates which operator to evaluate first, the exponent rules dictate how to handle same base powers, scientific notation handles the magnitudes, and estimation provides the final sanity check. Each skill has its place in the workflow, and the marathon teaches you the natural sequence so that you can replicate it on your own problems. Second idea, strategy comes before mechanics. When you see a complicated expression, your first move is not to start computing. Your first move is to recognize the structure, decide which rule applies first, and only then begin the arithmetic. Picking the right rule by sight is the single biggest skill that separates fast students from slow students on tests. The recognition phase usually takes only a few seconds once you have practiced enough mixed expressions, and it can save you minutes of arithmetic by guiding you to the most efficient solution path. Without the recognition phase, you might choose a long route that requires 3 times as many steps but still arrives at the same answer. With the recognition phase, you get to the answer through the shortest sequence of operations possible, which also happens to be the sequence with the fewest opportunities for arithmetic errors. Always end with a magnitude check via estimation. Even after a careful step-by-step solution, a 60-second magnitude estimate confirms that the final answer is in the right ballpark. The marathon problems are designed so that an estimation check catches any wrong turn made along the way, the same way the previous lesson on estimation taught. Magnitude checking never gets old, and it never stops being valuable. Here is the marathon strategy in one slide. The strategy is to pick the rule by what you see, not by guessing or by routine. The first move on every problem is to scan the expression and identify the highest priority operator currently on screen. That operator tells you which rule to apply first. Second rule of the strategy, PIMDS controls the order whenever multiple operations meet inside an expression. Parentheses first, then exponents, then multiplication and division as a tied pair broken left to right, then addition and subtraction as another tied pair broken left to right. The marathon problems will hit every level of PIMDS, often inside the same expression. Third strategy rule, when you encounter absolute value bars. The bars act exactly like parentheses around their content. Compute everything inside the bars first, then take the absolute value of the result, then continue with the rest of the expression. Treat the bars as a hard grouping symbol that respects PIMDS internally just like parentheses do. Fourth strategy rule. Whenever same base exponents meet, you have one of 3 rules to apply. Multiplication of same base powers means add the exponents. Division of same base powers means subtract the exponents. Stacking a power on a power means multiply the exponents. Recognize the operator between the two powers, then reach for the matching rule. Fifth strategy rule. Whenever the numbers are very large or very small, switch to scientific notation immediately and let the exponent rules do the heavy lifting on the powers of 10. Trying to multiply tiny decimals or huge integers in standard form is asking for an off-by-decade error. In scientific notation, the same arithmetic stays manageable. Sixth and final strategy rule. Always end with a magnitude check using estimation. Round each input to one significant figure, run the arithmetic on the rounded values, and compare the rough answer to the exact answer. If the two differ by 10 times or more, look for a unit error, a missed decimal, or a sign flip. The marathon flow always finishes with this magnitude verification step. Here is the first marathon problem. The expression at the top reads absolute value of 3 minus 7 plus 2 to the fourth divided by 2 squared minus the quantity 5 minus 9. This single expression touches absolute value exponent rules, parentheses, and the order of operations all at once. We solve it in 5 steps. Step 1. Compute everything inside the absolute value bars and inside the parentheses, treating both as hard grouping symbols. 3 minus 7 equals negative 4, so the absolute value becomes the absolute value of negative 4. 5 minus 9 equals negative 4, so the parentheses become the single number negative 4. The expression now reads absolute value of negative 4 plus 2 to the fourth over 2 squared minus negative 4. Step 2. Apply the absolute value definition to the negative 4, which gives positive 4. Apply the quotient rule from lesson 5 to the fraction 2 to the fourth over 2 squared. Same base, exponent subtract, so we get 2 raised to the 4 minus 2 power. The expression simplifies to 4 plus 2 raised to the power of 4 minus 2 minus negative 4. Step 3. Compute the simplified exponent. 4 minus 2 equals 2, so the exponent collapses to 2 squared, which is 4. The expression now reads 4 plus 4 minus negative 4. Notice the double minus, that is minus negative 4, which is the same as plus 4. Step 4. Resolve the double minus and add. 4 plus 4 plus 4 equals 12. The expression simplifies to a single number, 12. Reading from left to right, all three terms are now positive, so the addition is straightforward and produces the final value with no further sign manipulation. So the answer is 12. 3 skills came together in this one problem: absolute value handling, the quotient exponent rule, and careful arithmetic with negative signs. Notice each step removed one piece of structure without skipping ahead. That discipline of one rule per step is what makes marathon problems tractable. A common temptation is to combine two operations in one step to save time, but in mixed expressions that shortcut nearly always leads to a sign error or a forgotten operation. The slow and steady approach takes maybe 10 extra seconds compared to the shortcut, but it almost always produces the correct answer the first time, while the shortcut version often forces you to recompute the whole problem when an error surfaces in the final magnitude check. Here is the second marathon problem, mixing scientific notation, exponent rules, and estimation. The expression at the top reads the quantity 4.2 times 10 to the third multiplied by the quantity 7.1 times 10 to the negative 2, all divided by 2.0 times 10 to the first. Round each coefficient to a single significant figure, exactly as the estimation lesson taught. 4.2 becomes 4. 7.1 becomes 7. 2.0 stays at 2. The exponents on the powers of 10 stay the same. The expression now reads the quantity 4 times 10 to the third times the quantity 7 times 10 to the negative 2, all divided by 2 times 10 to the first. Step 2. Apply the product rule from lesson 4 to the numerator. Multiply the coefficients 4 and 7 to get 28. Add the exponents 3 and negative 2 to get 1. The numerator simplifies to 28 times 10 to the first, and the full expression now reads that numerator divided by 2 times 10 to the first. Step 3. Apply the quotient rule from lesson 5. Divide the coefficients 28 and 2 to get 14. Subtract the exponents 1 minus 1 to get 0. The expression simplifies to 14 times 10 to the 0, which is just 14. Step 4. Renormalize the 14 into proper scientific notation form. 14 is greater than 10, so we shift the decimal one place left to get 1.4, and we increase the exponent on 10 by 1 to compensate. The estimate is 1.4 times 10 to the first, which equals 14. So the estimate is 14, or 1.4 times 10 to the first. The exact calculator value of the original expression is 14.91, which rounds to 15. Our rounded estimate is correct to within 1 unit, which is well within the factor of 3 we expect from this method. The marathon flow worked around: apply exponent rules, simplify, renormalize, verify. Notice how this entire workflow ran without ever computing the exact decimals of any input. We did not need to compute 4.2 times 7.1 in standard form. We only needed to know it was approximately 28, and the exponent arithmetic took care of the magnitude. That is the power of doing scientific notation and estimation together. The precision happens on small coefficients, while the magnitude bookkeeping happens entirely on the exponents, which are integers and easy to handle without a calculator. 3 mistakes that show up over and over in marathon-style mixed expressions. Each one breaks the strategy rules from the concept scene, and each one is fixable by slowing down and applying one rule at a time. First mistake: skipping the parentheses pass at the start of the problem. A student looks at the whole expression, spots an exponent, and starts evaluating it immediately before reducing the parenthesized chunks to single numbers. That violates PEMDAS. Always do parentheses and absolute value bars first, then exponents, then the rest of the operations. The parentheses pass is the foundation that all the later steps depend on. Second mistake: a sign flip when subtracting a negative number. A student writes 4 minus negative 3 equals 1, treating the double minus as if it were a single minus. That is wrong. Subtracting a negative number is the same as adding the positive of that number, so 4 minus negative 3 equals 4 plus 3, which equals 7. Always read the sign of the subtracted quantity carefully, and always rewrite double minuses as plus signs before computing. Third mistake: mixing up the exponent rules under pressure. A student sees x cubed times x squared and writes x to the sixth, multiplying the exponents instead of adding them. The product rule says add the exponents when the operator between same base powers is multiplication. The multiply of exponents only happens for power of power, where one exponent is stacked on top of another. Read the operator between the two powers, then pick the matching rule. The skills that make up this marathon show up in any quantitative field. 4 real-world places below where you would use a section 1 mix without thinking about which lesson taught what. Unit conversion. Converting 3 kilometers to millimeters requires multiplying by 10 to the third to go from kilometers to meters, then by 10 to the third again to go from meters to millimeters. The product rule on the powers of 10 gives 10 to the sixth, so 3 kilometers equals 3 million millimeters. Without the exponent rules from lessons 4 and 5, every unit conversion would require manual decimal counting. Compound interest over many years. The balance after n years equals the principal times 1 plus the annual rate, all raised to the n power. Computing that requires exponents, multiplication, parentheses, and a final magnitude check that the answer is bigger than the principal. Every multi-year financial calculation is a marathon problem in disguise. Laboratory arithmetic, concentrations of solutions, pH values of acids, half-lives of radioactive samples, all involve scientific notation and the exponent rules to handle the very small or very large numbers that come up in chemistry and physics. A working chemist applies these rules dozens of times a day without thinking about them as separate skills. Sports statistics, batting average, earned run average, save percentage, and many other rate-based stats are ratios computed using PEMDAS to combine totals into a single rate. Then estimation checks whether the rate is in a reasonable range for the sport. Same skills applied at the ballpark instead of in the classroom. 3 things to take with you from this marathon lesson. By now you have all the Section 1 tools individually, and the marathon was your chance to use them together on real mixed problems. First, strategy comes before mechanics. The biggest gain in speed and accuracy on any algebra problem comes from recognizing the structure of the expression first, picking the right rule by sight, and only then beginning the actual computation. Students who rush into arithmetic without first scanning the expression are the ones who end up stuck or make wrong turns. Second, PEMDAS absolute value bars, the 6 exponent rules, and scientific notation are not 7 separate toolkits. They are one toolkit with 7 tools, and you choose the right tool by what the expression looks like. The marathon proved that the 7 tools cooperate seamlessly inside the same problem, with no friction between them. Third, always finish with a magnitude check using rounded estimation. The estimation check is your one-line guarantee against catastrophic errors. Even if the rest of your work is shaky, a final estimation pass catches any answer that is wrong by an order of magnitude. Coming up next, the lesson called Roleplay Pharmacy Tech, where we apply every Section 1 skill to a real-world workplace scenario. The numbers will be ugly, the units will matter, and the magnitude check will save you. The estimation pass is non-negotiable in any environment where the math drives a real consequence, like a patient's medication dose, and that habit transfers directly from the marathon work we did today to the kind of professional decisions a pharmacy tech makes every shift. Take a moment before moving on to confirm that you can apply each Section 1 rule cleanly in isolation. If any single rule still feels shaky, briefly revisit that lesson before tackling the role play, because the role play will combine 4 or 5 rules at once on a problem with real-world stakes, and the marathon was the last chance to practice combining them in a low-stakes setting.